Now let's take a look at some typical cache parameters. Notice that the caches range in size from 32K at the L1 level to 100 megabytes at the L4 level for those machines that have an L4. Main memory, on the other hand, tends to be between 4 and 32 gigabytes. It could be larger, but most systems have memory somewhere in that range. The distinguishing feature of the L1 cache is that it's split. That is, there is separate data and instruction caches so that they can be easily accessed in parallel. The L2 cache is unified. There's a single cache that contains instruction and data. The L3 cache is banked, which means that there are different parts of the cache, different addresses of the cache that are located in different parts of the chip. And L4 and main memory, of course, would be off chip. The access time ranges from 2 to 3 cycles for the L1 to 50 to 80 cycles for the L4, and main memory could be up to 400 cycles, certainly going to be at least 100 cycles. The implementation technology for L1 and L2 is SRAM, and below that typically DRAM. So, comparing centralized versus banked structure, what are some advantages of centralized? Well, the first is that movement of data between banks is simplified. But as far as we've covered in this class, the only time we've seen when data actually needed to be moved was in a virtually addressed cache, or virtually indexed cache, virtually indexed and tagged, when one process shares data with another process and there's a process or task switch between the two. Another advantage is that the interconnect between the L2 and the next level is simplified because it can be in one place. In a cache that would be distributed, you'd have to have parts of the interconnect all over the chip. What are some advantages of a banked structure? Well, a single tile can be designed and then stamped as many times as needed. So you can have the same kind of subsystem in many places on the chip. And that, of course, makes it easier to reuse across generations. Secondly, it's more feasible for a many-core processor where you can't centralize the cache because the wire length would be too great. You'd have too much of your chip area devoted to wires. And also that would heat up certain areas of the chip more than others, and therefore cause a cooling problem. So now I have a few questions about inclusion properties. What kind of caches move a block from one level to the other? Exclusive, because if a block is in one level, it can't be in other levels. Which kinds of caches propagate an eviction up from the L2 to the L1? Inclusive caches, because if a block disappears from one level, it has to disappear from other levels, from higher levels. Which kinds of caches have to inform the L2 about a write to the L1? Inclusive caches, because if a write is made to the L1, then that same data needs to be included in the L2. In an inclusive cache, can L2 associativity be greater than L1 associativity? It certainly can, but it can't be less than L1 associativity, or you wouldn't have room in the set in the L2 for anything that got evicted, or for everything that might get evicted from the L1. So now we want to look at a diagram of what goes on in inclusive, exclusive, and 9 caches. With an inclusive L2, if you have X and Y in the L1 and in the L2, and then you evict block X from the L1, because it's inclusive, well, it can stay in the L2. If a block Y is evicted from the L2, however, it must be evicted from the L1, because if it's in the L1, then it would have had to be in the L2. And then after an L1 cache miss on block Z, well, the Z gets copied up from the L2 to the L1. Okay, so in an exclusive L2 cache now, in the first case we see blocks X and Y in the L1, and so block X can't be in the L2. But after it gets evicted from the L1, it goes down to the L2. Then after block Y is evicted from the L2, well, it can stay in the L1 because it can be in one cache or the other. But after block Z, after there's an L1 miss on block Z, since it's an exclusive cache, when the block is fetched from the L2, it has to disappear from the L2 and then reside only in the L1. With a 9 L2 cache, we don't need to take any special action here. So X and Y are duplicated in both the L1 and the L2 as we start out. Then block X is evicted from the L1 cache and it can stay in the L2. Then block Y is evicted from the L2 cache. It can stay in block 1. But what the diagram shows is that Z somehow magically comes up to reside in the L1, and that's just a typo. That's incorrect. Z should not be in the L1 cache right here. And then, however, after there's an L1 miss on block Z, then Z would come up from the L2 to be copied to the L1.